might not be in a position to provide. What? You're looking for an opportunity to collaborate. Yeah.
Well, that's a good shirt. So I wonder where you got that shirt out. Did you look at a full convention of some sort?
If anyone needs help currently downloading, like installing Python or the libraries, just raise your hand and someone could help you.
If they don't uninstall it, I can run the server for them. How are you? Good?
Let's do that. Good? Yeah, Johnny, let's do it. Do that, Johnny.
Okay, yeah, for years, yeah, definitely.
Why don't you? I thought 3 is better. I mean, how's it? I've been on pandas ever since day 2. Yeah. Or do you need Python? Personal problem. Oh wait, do we get access to my profile? I'm not gonna no, because like if not, then I'll do my.
You guys can hit that address on your browser, and it should be running the notebook that you can follow along with on your laptop.
Yeah, but it's not really anything, but I don't think I have it installed. The guy who returned over there.
Yeah, you can do it with Anaconda too. Yeah, you can do it with Anaconda. Sure.
But I didn't open.
Yeah, I just don't want to like set up. But he's running
Yo, Adam, they can do the watch on that YouTube. Yeah, you can. Oh, I can do that.
That's actually a really good video.
Sure.
That's the one that has all the.
Do you guys have any umpire? Okay, we're gonna have a couple of quick announcements and then we'll start the workshop. Hope you guys are excited.
Hi guys! Welcome. This is our first workshop for the semester. So real quick, after this event, Google is also going to be here doing a workshop for them at 6:30. I forget the name. Yeah, at 6:30 from 9. There have been emails that have been sent out about it, so if you're on SCS, you should probably get that email. If someone wants to help me out, like, shout out the name, the room, that'd be appreciated. Secondly, our next...
Oh, here.
Oh, right here.
Yeah.
Woohoo! So you know where it is. Wonderful. Next one, the next upcoming hackathon that you can apply for, so I know applications for shell hacks are already closed, is Night Hacks. And you guys should look into that. It's in Orlando. It's in 2 weeks. It's going to be great. A whole bunch of us are going to go up and we're going to try and carpool. And there will be travel reimbursements for people carpooling together to get to the hackathon. It's going to be great. And lastly, of course, our workshop event schedule. We have workshops every Thursday from 3:30 to 5 in this exact same room. So without further ado, I'm going to pass you guys on over to Adam here, and he's going to get started with the workshop. Woohoo!
Alright guys, hold on, let me move to my screen. Alright, let's start. So this workshop is a intro to machine learning workshop. It's going to be covering linear regression. So it is going to be very primitive machine learning. It's kind of like the Hello World program, I would say, of machine learning. So, you know, if you've been studying this for a little bit, this might be very repetitive or basic, but it should be that for anyone who has not seen machine learning, I think this would be a good start. So here are a couple things that you need for the workshop if you want to follow along code-wise. So I think I'm expecting that everyone's coded before, so code isn't new to you. And then maybe some understanding of calculus will be important, and maybe a little linear algebra. But that's really all you need. The language that we're going to be using is Python, which is a very popular scripting language, and it's used a lot in data science. So it's really good if you want to get into this field to start working with Python. There's a lot of really cool libraries. One of them we're going to be using is NumPy. So NumPy is a numerical library. It stands for number in Python. And yeah, it's used a lot for scientific computing. And then we're going to be using Pandas, which is like a data frame library. So it's a really good way to handle data, to read data. So you can read CSVs or TXTs. And then we're going to be using Matplotlib, which is, it has all the plotting libraries I think that MATLAB has for Python. And so that's what it stands for, MATLAB Plotting Library. Oh, and then we're going to be using Jupyter Notebook, which is an editor. It's really cool if you've never heard of it. You can pretty much run code in blocks. So if you're doing any sort of data science, it's a really good way to test things without having to run just one giant Python script that's going to be like training or something like that. Because as your models get bigger and bigger, the training will get longer. So it's definitely something to check out if you're interested in this field. Yeah, so a little bit about me, if you guys don't know me. I taught this, last year. We did this workshop, I think, in the spring. So I'm a computer science major at FIU. I'm a senior. I'm completing my undergrad. I will be graduating in the spring. I do like machine learning quite a bit. I'm not an expert. I wouldn't consider myself an expert, but yeah, this is something I kind of fell into maybe like 2 years into studying it, and I was completely like obsessed with it for a little bit. And it's kind of crazy to see how just in like 2 years how the field has been growing so much. So we're going to talk a little bit, I think, before we get into the coding, about machine learning and the fields that they have, and then a little bit about the math, because it is a very math-heavy field in computing. So yeah, this summer actually, I interned for Target. I worked at a data science team. So I was doing some data engineering, a little bit of data science, full-stack development. I was pretty much like doing all the grunt work for the team there, and we were working. I was working in the merchandising division, and they're building this really cool engine that pretty much it's kind of building like a product recommender, but for their stores. So we're using a lot of data, a lot of forecasting data and previous data history to automate how we plan what the stores are. So we're doing this for every store, for every item, for every department. So this is like a huge thing Target has been investing in. And I think it's completed now, it's already out. The team I was on was called Apex. So I learned a lot from them. And yeah, that's kind of where it solidified that this is a field I want to work in. Currently, I'm working on a team with a bunch of FIU students, and we're building something called Guru. That another member of ACM is also on, and he started. It's an advising bot that we're building. So I'm going to show you so you see what stuff that I do. So it's an advising bot that you can talk to, and you can do things like. So you can do things like look at the flowchart for CS, and we're going to build a bunch of different cool things and trying to make the bot as smart as possible. So that's something I'm doing now. Yeah, I think it's pretty cool. And yeah, why learn machine learning? So I think everyone here has probably heard the word machine learning. It's pretty much a buzzword right now. Like I think the word machine learning and like big data is kind of like really big buzzwords, and like people who are making startups are like, that's kind of the first thing they'll say if they want to get funding, and a lot of like, it's like a really popular thing. So yeah, the field is growing, and like a lot of really cool stuff is happening. So I think now everyone's aware of like self-driving cars. Amazon had their employee-less grocery store. So there's like a lot of different really cool things. And I wanted to show you some links that I found of like very recent things, specifically in the gaming world, that is going on. That's really kind of blowing people's minds. So, is everyone familiar with Go and DeepMind and what happened? We're all familiar with that? Okay, cool. Yeah, so that's a big thing that a huge development in AI, and they did a really cool thing with a paper on something called Q-learning, which is using machine learning to play video games. So it's pretty much teaching a game from no experience how to learn to play a game, giving it some sort of like objective function. So really cool things like this, where they become masters of after like only a little bit of training, they learn a lot. So yeah, that's something like that. And then there is, I don't know if you guys are familiar with the company called OpenAI, which is a research company based off in Silicon Valley. And they recently won 1v1. They beat some of the best players in Dota 2. So there's this thing. Oh, you can't really hear it. So they trained the bot in only 2 weeks to play some of the best. Oh. It's really cool.
Guys, let's give him some words of encouragement.
What's that? Anyways, you guys can see. So this is a bot, and it's really like they trained it in 2 weeks, and it learned how to play and beat some of the best players in Dota 2. So yeah, this was a huge advancement because no one really thought that you can win this game because there's so many different parameters to learn, and it had like this really weird technique where it would accept a lot of damage early and kind of lower your guard, and then it would like destroy you in like very little time. So I actually don't know this game, so if maybe someone's like way more interested in this, I know this is a huge thing. Yeah, so. And then there was another thing that was actually very recently that someone showed me, is that they're training a new type of deep learning method to break CAPTCHA, which was one of the Turing tests. So this was actually really cool because AI can very easily be confused by like little changes in words and stuff like that. So it learned how to do that, and this is just like something that I think happened maybe 2 weeks ago. A paper was published on it. So yeah, the field is really growing very fast. So there's a lot of cool things to learn. Yeah, and also you can make a lot of money in machine learning. So this was last year that I found this. So data scientists / machine learning engineers have a market salary about $135K, which is quite a bit, I would guess. And there's a lot of companies that are really investing heavily into machine learning. So like Google, Amazon, Microsoft, they're all expanding their departments. And now when you go see a recruiter, they're going to talk to you about something that they're doing in AI. Like everyone had I was at the JP Morgan thing yesterday, and they were talking about their machine learning department and how they're growing it over the past year. Yeah, so then I think the next thing is like really what is machine learning? And does anyone have like a definition that they can give about machine learning? Anyone? Oh, you got one? Okay, what's
Learning from experience and data itself.
Yeah, that's a good one. Anyone have another definition that they have when they think of machine learning? That's a really good one. That's probably that's like a pretty good definition. So Arthur Samuel said, it's a field of study that gives computers the ability to learn without explicitly programming them. So that's like the main difference of what just regular programming, where we set rules on what the computer should do. With machine learning, we train a series of weights, and those weights are kind of what is programming. So that's the main difference. So there is a famous quote that's kind of confusing. It's a computer program is said to learn from experience E with respect to some task T and some performance measure if its performance on T as measured by P improves with experience E. So this is a lot of things where you expose it to a data set, you have some sort of measure of performance or a loss function, and we're going to learn more about that. And that's kind of how machine learning is in all different type of fields, whether it's linear regression, which is what we're going to be learning now, or classification or anything like that. So and yeah, there's two major fields, I guess, in machine learning. So we have supervised and unsupervised learning. Is anyone familiar with these terms, supervised and unsupervised learning? Okay, cool. So not a lot of people, I guess. So supervised learning is the machine learning task from inferring a function from supervised training data. So we have an input and we can directly correlate it to an output. So that's something like linear regression, classification, neural networks. Those are really big. And then in some unsupervised learning, we're trying to infer on data that we have. So something like clustering, document clustering would be one, recommender systems are another one, like Netflix's recommender systems, and anomaly detection is another one, where we don't know the specific correlation from X to Y, but we're trying to infer on it using machine learning. Alright, so now we're going to actually talk about linear regression. And I'm sorry if it's like kind of weird because I feel like I'm in the middle of this whole thing. So, do you guys want me to stand over like, here's fine for everyone, right? Yeah, cool. Alright, cool. So linear regression is just a relationship between two variables by fitting a linear equation to observed data. And the problem that is to predict a real valued output. So the difference between like linear regression, logistic regression, or classification is that with linear regression, with regression is that we're trying to predict a real number. So something like housing, predicting housing prices is a very popular one because it's a real number that we're predicting. We're not predicting a class. So we use a set of inputs, known inputs and outputs to make a predictive model to output the new data. So we can have a bunch of different features for this, and we're going to be going over predicting prices using square feet. So something like our inputs, what would inputs be if you want to predict the price of a house?
Square footage?
Yeah, square footage would be a big one, right? Location would be a big one. Yeah, that'd be a really interesting one because how do you model location and what makes a location better? Yeah, that'd be really interesting. And any other one? What?
Interest?
What do you mean by interest?
Like interest, like for example, like you know how they're scaling up the interest for houses.
Okay. Okay, cool. What else?
Number of bedrooms.
Number of bedrooms, yeah, that'd be a big one, right? Also, like if it has a pool, number of bathrooms, right? Bunch of different things. When was it built? So like you can definitely scale up the features and see what features you think are important to predicting the price. And that's kind of how the art of data science, I guess, is knowing what features are working really well. So yeah. So right now we're just going to be using square feet. and to predict the price. I think actually we might use bedrooms too. But we're going to do one thing where we're just mapping one value to an output, and then we're going to do things where we map two values to an output. So that'll be linear regression and multivariable regression. Okay, cool. So let me see if I can write on this thing, because last time we did it, I wrote, and I think that makes it way easier. Everyone sees that, right? Okay, cool. So, it's kind of weird talking like this. So if we have kind of a correlation from square footage, I guess the whole point of linear regression is if we have, let's say this, I do not know how to use Windows. There we go, we got it, okay. So my handwriting is so bad. So let's say we have square footage, right? And we have price. So we have this, right? So let's say we have this little like price is going up there and square footage goes up. Does that make sense to everyone? That's cool, right? It's just some like ghetto graphing right now. Okay, so I think we can all assume that as price goes up, as square footage goes up, the price will go up, right? That makes sense. So we can probably, let's say down here we'll have like a couple of prices, but we can definitely, if we see some sort of correlation between prices and square footage. So it's not always going to be a perfect correlation, so maybe something could be right here, and that's definitely going to affect our model. But we can definitely say that as square footage increases, there is some correlation between prices. So with linear regression, the whole objective is to find a line to predict, to give the best predictions, right? So if we have a bunch of different data points on square footage to price, we want to make a line that will give us a prediction. So every time we have a new house, we can now predict the price. Or for anything, this is kind of generalized to any regression model. So there's, the first thing to do is to how do you know what's the best line? So if I had like this line is kind of an easy question. Maybe like this line. Oh wow, that's not good. What's the best line if we see this right now? Which one would we say? Just shout out the color.
The thick pink one.
The thick pink one, yeah, that's that's the best line. So yeah, the red one is the best line. How do we know the red one is the best line?
Because the one that hits the most points.
Looks like the average.
The most houses, whatever.
Yeah, right. It looks like it looks like it regresses to the mean, right? Yeah, so it's kind of the one that we would think would be the most accurate representation of the data, right? So I mean, and there's different ways that some people can they can argue that there's different best lines. So I think a good argument that people have is that you might not want to undersell your house, right? So fitting a regression model that takes in that you don't want to undersell your price or oversell. So you don't want to give, you don't want to train a model that oversells the price of your house. So maybe the people will not buy it because it's too expensive because the model predicted unrealistic cost. So that's a big thing to keep in mind. But for now, we're not going to give any weight on what's more expensive, like where the line gives. Does it give preference to more expensive ones or not? So we have this thing. It's kind of messy now, so let me erase it. So we have like our data points, and now we want to automate how. Oh really? Trying to save paper. So we have square footage, and we have price, and we have all these data points, right? And we want to know how how to choose the best line. So we need some sort of way to represent what's a better line than the other one. So let's say we have this line, we have this line, and we have this line, and here maybe like to your eye, there isn't maybe a exact grade line that you can tell, right? So I think then the next question would be, how do we represent a good line? Does anyone have like an idea besides you? Because you were in the last one.
What's a good line?
Yeah, what's a good line?
Well, I mean, it depends on your perspective in a sense, right?
Yeah, that's true. But if we're trying to model this with data,
With just data.
yeah, with just data. Does anyone? Oh, cool. Yeah. What's up, man?
Could you minimize the distance from the points to the line?
Yeah, that would be. Yeah, that's exactly what it was. Nice. Yeah, so that's how we would make maybe a cost function, right, or an error function. So given our line, whatever arbitrary line, the distance between the actual points that it predicts, how great is it, right? So if we have, even let's say I could make it a little smaller. So if we have just, let's say, a couple dots here. We have a line like this. The distance would be kind of how we measure how good our line is, right? So something like this, there's maybe a small distance or smaller distance compared to a line like that, right? Where there is way greater distance between the line that we make and the data points. So now I guess the question is, how do we represent that in data? So I'll go back to my slide because I have the answer to that there. So, yeah, okay, yeah, so I forgot to mention this. So, no, I'm mentioning that after. So, if we have the goodness of our fit, is what it is called, is a cost function to test our predicted values against our observed values. So if we have some sort of line, we want to see our predicted values and how does it measure to the actual values in our data set. And that's kind of how, that's maybe the first step of machine learning is now we've kind of have a cost function. So we're saying with the line that we made, how well does it fit to the data points? So a line that like is kind of going straight horizontally will have a worse measurement or a higher error function than, let's say, the line that's on the graph. So there's a couple ways that you can measure this, but this one is called the residual sum of squares. Does that make, has anyone heard that word before? Residual sum of squares? Okay, cool. Yeah, you guys heard it? You've heard it before? Okay. So yeah, the residual sum of squares is just that we take our predicted line, subtract it to the real values, and we sum the square of them. And then, well, we divide it by the size of the data set. So that's because as our data grows, we don't want to have the error cost grow, because then like more data points will then cause a higher error loss. So we divide it, kind of find the average of it. And then the 1/2 is because we're going to take the derivative of it. But yeah. And let's see, what else do I have? Yeah, so then we take the sum of it too. And why do we square it? Does anyone know why we square it?
Because it's hard to take the derivative of absolute values.
Okay, yeah, that makes good sense. But like, why would we take an absolute value? Yeah.
When you do square, you get rid of your half that you have.
Yeah, but like, why? Let's say if I didn't have a half and I didn't square it, what would there be a problem?
Negative?
Yeah, negatives, right? So we would be subtracting as well as adding to the cost. So then, let's say if we have a line, all the data points below it would be negative, and then therefore, like our error function would decrease. So that's why we square that makes sense. Yeah, and the 1/2 is for when we take the derivative. So we can represent our line in data as, or our hypothesis as a function where we take one input and multiply it by a weight, and then we take a bias. And a bias is just, well, there's different things. You can have regularization, but a bias is just a weight that doesn't correspond to any actual feature. Yeah.
Like for example, in a house price, it could be considered like the base price of a house.
Yeah, I guess so. Yeah, you can consider that. Yeah. Yeah. Mm-hmm. Yeah, that's a good example. So right now, with our hypothesis, with our model, we are having a correlation from size to price. So that's why we have this one weight, which is I guess theta 0, which is just a bias number weight, and then we multiply the x input times theta 1. So what is x in this? Yeah, the square footage, right? And then that's going to give us, the function is supposed to return a price, right? So that's how we're going to represent our model. Is just theta 0 plus theta 1x. And as we grow with other input features, we will grow. So we can have theta 0 plus theta 1x plus theta, well, I guess theta 2x2, you know, and so on. So as features grow, every feature should have its corresponding weight. And then with that, we can have our cost function, which is just then our predicted, our hypothesis is what it's usually called, minus our prediction squared, and we take the sum of that, and we divide it by 2 times the length. So does that make sense to everyone, the residual sum of squares? Because that's probably error, making an error function is maybe one of the most important things to understand with machine learning. So we're all good with that, right? Okay, cool. So, yeah. So then the next part is, so we have our cost function, and what do we want to do with our cost function? Like, what's the objective with the cost function? Yeah, minimize the errors, right? So we want, right now, okay, there may be things where you overfit, which we'll talk about later, but right now we just want the lowest cost function, right? So we want the line that fits the data point perfectly. So now we need to have some sort of objective to minimize cost function. And there's a way to do it easily with calculus. Yeah, so here, right here, is, you can see kind of a cost function where we map all the values of theta 1 and theta 0, and then correspond to the cost function of theta 1. So we can finally we have some sort of local minimum, and that's kind of what we're trying to achieve, is to reach a local or global minimum. And that's then where gradient descent comes in. And we're going to code this all later. So this is just trying to understand the theory. So with gradient descent, we can take the derivative, the partial derivative of our cost function, and we can descend down to reach a local minimum. And I'm going to switch back and kind of show why gradient descent or taking the derivative will reach down to a local minimum. Does anyone know why we would use it to take the derivative of a function? I know there's like maybe a couple of math majors here. Why would we take the derivative of the cost function?
Oh, I know the answer, I don't remember. Would it be to find the direction where it's at its minimum?
Okay, yeah.
Rate
Okay,
of
yeah.
change?
Yeah, the rate of change, exactly. So, yeah, so maybe I can draw it here. So we have like some sort of function like this, and we had plotted some sort of point here. If we find, maybe like right here, we find the tangent line here, we can see that the rate of change, and the objective is then to find where the rate of change, the tangent line, is 0, right? So with taking the derivative and using calculus, we can then descend down and find the cost function and see whether we need to subtract or add to our weights. and then descend down to a local minima. So I think that right there is probably the most confusing part of the machine learning. So does everyone understand why we're taking the derivative of the function? That makes sense to everyone? Yeah. Yeah, so what we're trying to do is we're saying, okay, let's plug into these, let's take the derivative of the function and let's try these weights, right? And if these weights will then give us some sort of update, right? Once we take the derivative, we find the rate of change. So if we're up here, then it's going to be a high rate of change. And then what we can do is we can take this, the derivative, and we can subtract it to the weights. So then we can descend down the function, or the cost, this convex function. And we can do that, and if we go here, then we would add to it, and here we would subtract to it. So that's kind of what descending down the gradient is. So you take the derivative of the function, you try it with those weights, and then you can update those weights. And then achieve two weights, which will give you, the lowest error cost. So going back to here, so this is kind of what the algorithm looks like. So we reach until we have a convergence, and that's just theta j. So depending on how many thetas we have, is equal to theta j minus alpha, which you see there, which we'll talk about a little bit, times the partial derivative of the cost function. And right there, that's pretty much the hardest thing, I think, in machine learning is optimization, and that's our optimization function right there. So for each weight, we are going to take the partial derivative, and we're going to subtract that. We're giving a step to our theta, and that's how we update theta again and again. And so we have an alpha thing that I have not talked about that. What do you think that is for? Yeah.
That's the rate at which you want to learn?
Yes, exactly. Yeah, so the reason why we do that is because if we just subtract from the derivative, we might overstep, and then it's kind of weird going back and forth from here. So if, let's say, you have like that function that we showed, and we just updated theta, we would then jump to the other side of the function, and then jump to the other side of the function if we have these really high updates, right? So if we have some sort of small update, so theta is usually a small number, like 0.01, 0.03, then we can update slowly and converge slowly, and then guarantee that we reach a local minimum. And so like, that's kind of another part of, it's considered a hyperparameter, and that's kind of where you get into, I guess, the art of machine learning and data science, choosing a correct hyperparameter. But those change, and there's different optimizations that kind of, they decay as they go down and get closer to a local minima. So yeah, there's definitely different things that you can go, but I think that might be beyond the scope of this talk. So I guess let's take the derivative of this cost function. So going back to here. So we're gonna do some math. So if we have, so if we have our cost function, and it's so our cost function was, what was it again? Does anyone remember it? No. Yeah, so it's 1 over 2m times the sum from all the data points, where so equals 1 to m of our hypotheses, which is h of theta, where the data point from I minus y of I squared. And remember, keep in mind that h of theta is equal to theta 0 plus theta 1 times x. Cool, so this is our hypothesis right here. And so we're pretty much just taking that, for every data set, every data point that we have, and we're subtracting it from its correlated output, and then we are squaring it and taking the sum of it, and then eventually we divide it by 2 times n. So if we took the derivative, the partial derivative, does anyone, I don't know, like I don't think everyone has taken calculus 3. I haven't taken calculus 3, but the partial derivative, if you have, let's say, two functions, you have theta 0, theta 1, you would take the derivative of theta 0 and you would treat theta 1 as a constant, and then you would take the derivative of theta 1 and you would treat theta 0 as a constant. Okay, yeah. We're going to take a break, pizza break soon, and then we'll code it up. So let me just finish this part, which I feel like is the most boring part. So, alright, let's just take the derivative of this. So, if we have this, I'll write it out again. So, for partial derivative for would be then, so you have to then, since this is, you take the derivative of the outside function and take the derivative of the inside function, right? So it would then become 2 times theta 0. Oh no, I ran out of space. Okay. Let me write this one. Yeah, maybe down. Okay. So it would be then 2 times theta 0 plus theta 1x. So we took the derivative of the outside function, and now taking the derivative of the inside function, what would it be?
4.
No, not 4. So what would the derivative be of x if you were taking
Respect to what?
respect to, let's say the respect to theta 0 in this function, and theta 0 plus theta 1.
You get a constant.
Yeah, you get a constant, right? So it would just be times 1. Oh, and I'm missing minus y. So there's a y there. And then, so that's for the derivative of theta 0. And then for theta 1, it would be then the same thing as the outside function. So 2 times theta 0 plus theta 1 x minus y, right? But then we take the derivative of theta 1, and what would it be? Times x, right? So we have now the partial derivative of that, and the partial derivative of theta 0 and theta 1. So then we're going to be using that, and we'll just repeat this for every single theta that we have. And we will just say then, for the algorithm, it is theta 0 is equal to theta 0 minus alpha. So when we brought down the 2, the 1/2 cancels out, so we have over m times the summation. It's a really bad summation. Of h of theta minus y times 1. Where did it go? Times 1. And then theta 1 is equal to theta 1 minus alpha times 1 over m x. Right? So that's our gradient descent for this problem. And then we will now code that up. And you're going to do that, and you repeat that until you reach the convergence. And there's definitely different ways to describe convergence. What would be one way to, I guess, describe converging? Like, how do we know how long we do this for? Yeah, but if we reach a local minimum, I guess as time's on, we can iterate and iterate and iterate. Yeah, but I guess as iterations grow, you will get closer to a local minimum until maybe you get stuck. But I guess what I'm trying to say is that, well, maybe you can have a certain conversion threshold. So we say we'll repeat this until we get to this sort of threshold, right? Or we can just train it for a number of times, right? We can give it some arbitrary thing, train it, and then see what our error function is. If it's still low, and there's different ways to measure performance. But if it's low, maybe we can train it for a couple more iterations, and just figure it out from there. So yeah, so that's all the theory of it, which is kind of painful. But now that you guys have all the theory, we can code up a simple machine learning linear regression program. So yeah, we're getting to have pizza, and then we'll code up the rest of it. Cool.
Just one thing. So I have a bad news and a good news. Which one do you guys want first? Okay. The bad news is that we didn't order enough pizza from this round. So I'm going to ask you guys, please just get one slide. The good news is that we have more pizza coming. So, the other pizza we get here like in 15 minutes. So just try to get one slide. Let's try to get everybody to get at least one slide, and then later on you guys can get more. Okay. And also refreshments are on their way too. So thank you.
The pizza's over here. Make sure to sign the sign-in sheet if you haven't.
Also, if anyone has any questions so far, you can come here. Ask Adam. He's gonna be here. He's probably not eating pizza, so if you have any question, come here and just ask him whatever question you have.
I don't know if you know.
Yeah, you got it.
No, I never took it. Yeah.
Just be like, hey guys, have any questions about any other events?
Yeah, but I mean, I think once you understand, once you understand, like, I guess the basics of it, you don't really need to understand it. That's kind of just like, just so you know why we're doing this, right?
As you know, like regression library, well, I have my own machine learning library. Yes, I can learn. You can just pretty much call it the regression function. Yeah. There's a program that you can install 10, 15 lines. The whole regression.
I think so. It's not.
Thanks.
I really like all the requirements on the whiteboard. The same one that you do. All we're going to do is since we create all different scenes of marriage, Yes, we are. So,
Oh, yeah.
So you know like that the ass this year.
I don't read the second yeah, it does. I just noticed it. Yeah, for
follow
so
over
like,
there.
yeah, for one variable, yeah, you could. Yeah, and then there's ways that if you do that, I don't pass one variable.
I'll let go.
What? Well, yeah, I'm trying to come back and then or just like, yeah, it is, it can like,
What's my hat now?
but no.
No, but that's it. I mean, Mark is
He's probably getting.
All right, so just in time. So just in time, the other set of pizza arrived. If you haven't gotten any, get now. Wait for those yet. Whoever hasn't gotten pizza, please go now get. We also have refreshments there now, so if you're thirsty, you can go there. We have Coca-Cola, I believe. And then after the people who have not gotten pizza yet, then everybody else can get round two.
Was it a side thing or did you guys figure it out?
No, yeah, it's like, I don't want to. Yeah, no, I did not think.
Where were you taking it?
No, I don't. Yeah. Yeah, everything is on. Yeah. But this is the extent that you'll go to. Yeah.
But it's not just
My hat for me.
or you have to have the 46 pages.
Yeah, then you put it, so like instead of tracking
Please sign the sign-in sheet if you haven't. It's still over there by the pizza. It's kind of full, so you have to go on the back of the page, but yeah.
Or you give me
My phone's really laggy. But it didn't work first.
Oh, you think like higher?
So you win this one.
I'm gonna talk about it on a slide, but no. Not for this
This out really?
part.
I didn't exactly.
Half an hour. But I do go over like. I mean, is it? Oh yeah. Like overtraining. Because you see the thing is like you're trying to you have the data set. So when you have like bias and you're overfitting the data set, then like you pretty much don't have like what's the point? Yeah, it's pretty much memorizing the data set. So there's definitely I would have take the sum of the data and you add that. So it comes it's something called untrainable data or untrainable error. So you have something called like trainable error and not data is supervised. It's so supervised learning is just a type of machine learning, right? So most things in supervised learning will have some supervised and there's different ways. So like in neural networks, they use dropouts. Yeah, you drop out some specific. And then there's ways that you can see. So if you like your training data has a very high accuracy for something, but then your testing set has obviously overfitting, right? And there's just different ways. So that's kind of when you get into like that's kind of then like the art.
One more thing. I hope all you guys are doing the pizza, but if you can please clean up after yourselves. Technically, we're not supposed to be here, so if we leave a mess, we're gonna get in big trouble. So please throw all the garbage away. We have garbage cans over there. If you see garbage, Okay, so over there and over there, and over there too. So if you see garbage, pick it up, please throw it away. Clean up to yourself. Thank you.
Yeah, that's
the biggest garbage we have. That's not recyclable. That's complete waste.
Basically, the function that we define with the residual sum of squares. So then we take the derivative of the cost function to establish the rate of change, and then we update the weight. We're using a step because the stepper function will like ensure convergence. Because if you just subtract the derivative of the function, then you might overstep and not reach a value. Because if you're like almost you go in here. So let's say you have like a function that we're talking about, right? And then you have a high stepper. So let's say you update the weight, and then that brings you here. And then you update the weight, you can actually even bounce the ball back. So with a stepper, then you're saying, okay, I'm going to get a fraction of the update, and then it'll be a slow conversion. You're kind of taking these tiny steps, and it'll converge faster. Not that long. Well, yeah, you want it to converge up to a linear. Because this is your error, you want it to do something. Yeah.
Oh, you remember me? Oh, that's completely made a picture.
Yeah. So like this, yeah, there is concavity, right? Okay, yeah, I'll come to that right now.
Alright guys, so we're gonna code while you guys eat pizza. So I'm just gonna code through everything and we should get some cool outputs. Not really, we're gonna get some graphs, which are gonna be awesome.
Nice.
Alright, oh shit.
Don't die on me, man. Yep.
So if you're unfamiliar with Python, it's pretty much just like coding in the English language. It's very simple. So there's a few libraries we have to import. Can everyone hear me like this? Is that fine?
Yeah.
Should I speak in the microphone? Cool.
There's people all over there, dude.
Oh, can you guys hear me back there? Okay, cool. Everyone can see that. So this is Jupyter Notebook. If no one's familiar with it, so you can do some cool things like you can just run blocks. So you can do like x is equal to 4 plus 7, and then you can like print out x. But then I can just do like I can change it here. And you have, if you run the block, then so you just pretty much run code in blocks, and you can specify how many blocks of code you want. So the first thing we're going to do is just import some libraries that I talked about. So these are our import. So we're going to import NumPy. We're going to import pandas. My S key sucks. I don't know why. So, and then we're going to go from Matplotlib, Python, import, no, sorry. Yeah, import, sorry. Not from. So, import, Mat, then Python. And we're going to use this library to just plot data. So the first thing we're going to do is I have this data file right here. So I think we might not have time to do the housing prediction. So this is actually this data set is predicting a correlation of population to profit. I don't think this is an actual real data set from anywhere. What is really good about it is that the data is normalized, so we can converge quickly. And there's a pretty visual correlation between the population and the profit. So we're going to use that. So we're going to use then pandas, which is our PD, to read. And it's going to be the example in text. There's no header, so we don't need it in the CSV file. And yeah, we can give names to it. So oh, also this data all comes from the Stanford Coursera course, which I took a couple years ago. So if you guys want, you can just sign up for the course for free on Coursera, and you can do all these things. And the professor who teaches it is this really famous machine learning professor named Andrew Ng, and it's kind of like the canonical course. So that should be it to read our data. Oh no. Oh, sorry, read it. Sorry. Nice. So now we have our data. So we can look at that. So there's 97 examples. This is our population, this is our profit. And we can plot it really quickly. So you guys can get a So everyone can see here the correlation, right, between population and profit, right? So as population increases, this is I think in thousands, profit is increasing. So I think it's just trying to say that bigger cities make more money. So now what our objective is to fit a linear regression line to predict population size and what the profit would be. So there's really only two functions that we're going to need. Can anyone guess what the functions are going to be? Yeah, so we're going to have a cost function, and then we're going to have a gradient descent function, right?
Yeah.
Yeah, so those are the two things we're going to have. So I'm just going to do cost function. This is going to take our x, our y, and that's theta. And it's going to... So this is how you create a function, and you just define it like that. So we're going to make a prediction is equal to np the power, because we're going to square it, right, of times theta transpose. We're transforming just because you're multiplying two matrices. So let's be minus 1. To return the sum of this. Should I zoom in? Is that better? Yeah. Yeah. So 2 times the length of x. Cool. So this is our residual sum of squares. So right here we square the prediction, which is our hypothesis, which is our inputs times our theta values, and then we subtract it by our predictions, and we square that. And then we take the sum of our predictions, and we multiply it by 2 times the length of x. Cool. And then now we need a couple things here. So we're going to add a column of ones, and since we're short on time, the very fast explanation is that we're going to have a bias function that we need. So the bias function, we're going to, it should be times, not like it's just going to be added by itself. So we're going to add a column of ones, so we will just be multiplying when we do the dot product of the x times the theta values times 1. So then the bias function stays the same. So data should now look like this. So we have ones, population, and profit. And now we're just going to separate. We're going to separate into data state. Our x and our y. So we want the first 2 columns of our x input. There's 1, and then we want. If I'm making any like syntax errors, or just errors in general, let me know since we're short on time. So columns -1. Alright, cool. So these work. Cool. So now look, this is our x input, right, which is our population and our ones, and here's our y, which is our prediction. Our output. So now we're going to. So we're just going to change this into a NumPy matrix because NumPy allows us to do a lot of linear algebra function on this. I'm going to go ahead and do that. So I'm going to do y is equal to np dot matrix y values, and then we're going to call theta is np. It's a matrix of just, we're going to initialize them already initially to zeros. So theta will look like this. And now x looks like this, and then y looks like this. Cool. So first thing we can do is compute the cost, so we can see what our initial thing is. Oh, sorry, cost. With x, y, and theta. And so we get some value here. So this is just our first run of our error function, which is, so it's 32, and that's good because that's what it's supposed to be. And then we're going to do the last function, which is a gradient descent. And that's going to take x, y, theta, alpha, and a number of iterations. And so I'm going to have a 10. Let me just write in quickly so then I can. Just take some time. Since we only have one copy. So this is the function that we have, and I'll walk everyone through it. So right here, we're just setting up some variables because we're going to have to store theta into a temp and parameters is just the number of theta weights that we have. So what we do is we're going to iterate through the number of iterations that we want to choose, which we'll choose 1,000. And we will just make this error function, which is back to our gradient descent algorithm. So it's x times theta transpose minus y. And then for each parameter that we have, we're going to multiply the error with its corresponding weight. So how we found the gradient, so the first one is times 1 for theta 0, the next one is times theta x. And then we just update that specific theta. So it's going to be theta, so theta, as we said in when we wrote, is theta minus alpha times the length of x plus the sum of the derivative of the cost function. And then here, I'm going to use this for some graphing later, which is so we can show how, as the cost goes down, we get a better accuracy or a prediction. And since we only have 10 minutes, I think I have to copy code.
Why not just show that one?
Yeah, that's true. Okay, so let me run it again then. This is my cheat code. So yeah, we computed the cost. We had the gradient descent. So I call my alpha 0.01, so that's how it is. That's not arbitrary, but it could be 0.03, it could be 0.05. You could have it at a greater thing and kind of reduce it as time goes on. And we're going to do another arbitrary hyperparameter, which is 1,000 iterations. And then we run our code, so gradient descent. So we're getting our cost, which is it's just our cost is just every time we ran the gradient descent, we store what the error is. So that's just for visualization of a graph. And then we have this g, which is our final theta weights, which is this. So these are after 1,000 iterations. These are our final weights. So theta 0 is negative 3.2. So I'm guessing it's saying that it takes the base cost is pretty low. And then we multiply the cost of the square footage by 1.12. So these are the parameters that our algorithm came up with. And if we plot the line, this is the line that we get. So as you can see, it's pretty, I guess it's pretty cut down the middle, right? So we see we have a lot of data points here, and it kind of gets in the middle, and as things it grows, it pretty falls like pretty much in the middle. And then I can run it maybe a couple more times. Let's see if I run it 10,000 times. So very little change. Yeah, very little change. And then here right now I'm just plotting the iterations, so that cost list that we have. So after every iteration we can see, so the cost goes down, goes down, goes down, goes down, goes down. Oh, this is because I have it 1,000 times. So it has a lot of cost down and it goes down all the way. So we kind of reach some point of convergence, as you can see. And I guess I do not have time for the housing thing, but I'll host this code on GitHub and we can put it on ACM website. But that's pretty much it. That's the machine learning linear regression algorithm, just using NumPy, no libraries. So hopefully now you guys have some tools that you can use and build up off of it. So thanks, guys. If you have any questions, I'll be outside.